Welcome to the course on FPGA based signal processing systems. We'll continue with the modeling of digital circuits, and we'll also look into test benches, how to write test benches today. And considering the modeling which we have done in the previous lecture, so the structural model and the data flow model, the behavioral model. So the Verilog modules can be made for the digital circuit modeling, structural, data flow and behavioral. So we'll see some few examples and the test benches, how to write the test bench for these modeling, and few more insights of the instantiation of module inside a module, which is usually done in the test bench as well. So the syntax for the Verilog instance statements, that is when we call a component or a gate inside a module or instantiate a component in a module. So the first name is the component name. For example, the AND gate and the OR gate, as well as the built-in gates we did in the previous examples. The component name and the instance identifier, that it has an identifier, the name which we give in the local digital circuit, and the expressions continue within the bracket. So this is one format in which that we instantiate the component, and the second format is the component name and instant identifier. Also within the bracket we have the port name, dot port name, this is need to be noticed, dot port name and the expression, that is the local expression, also a comma, dot port name, expression, and it continues within the bracket. So this is format 2. How do we call a module inside a module? So that part we look into the instantiation examples. For example, this port association of format 1, so in which that the order, if you have just looked into the previous examples, and we'll have more examples as well. So the AND gate, for example, that AND gate we had this AND and the optional gate name, whatever this G1 or G2 or G3, and there is an output Y and A and B. So this is the way in which we are writing. So the output followed by input. So the order in which the built-in gates are defined. So the order in which the expressions are written matters. In the case of component name, the first format, so the order should be in the same way in which the components built-in gates definitions are. So it is particular very important to note is the same order. The built-in gates, the order is output and then input and then input. So if you have multiple inputs, from input 1, input 2, input 3 and so on, the input order doesn't matter, but it should start with the output and then input 2, input 1, this can be in any order. So if you have the multiple input gate, so that can be put it in the in any order. So usually we put input 1 and input 2, and so multiple inputs, it doesn't matter, but then calling name, that output comma input and input 1 and input 2 it should be in the same order. And the built-in tri-state buffer, suppose it is going to be a buffer which has tri-state, which is having the enable input as well. So this enable input can be a not active low also. So this X and this is Y and this is considered to be an enable input, in which when you instantiate this type of component, then the order is output and the data input, which is X over here, and the enable input is the E. Yes, the output is Y. So the instantiation of this component should be in this order: output, data input and enable input. This is for the format 1. All built-in gates would be following the format 1 of port association. If we take the second format, in which the port association can be listed in any order. So because that is a Verilog module, suppose you have made, and which is given as module, and there is an end module which has module name and the port names. So the port name 1, 2 and 3, so on. This is port name 1, port name 2, that is port name 2 and port name 3. So then this also assuming that these also contain the declarations, and then the statements continues, that is, so the order in which this port name, maybe it is input and then output, are the output and input. So this, whatever the list, the list of port names, they can be followed in the association. So which has dot port, dot port name, whatever that the syntax is dot port name, and in the local expression what we call that net is, or the output is. So we will see them with the example. So this can be in any order if you call a module inside a module. So these are two formats for port association which is followed in the Verilog. This is the syntax for it. Now consider the one example which is for the structural model. So we have in the circuit shown in figure as the x1, x2 and x3, x4. There are 4 inputs, and you have the outputs are G, H and I, in which they have the OR gate 1, OR gate 2, AND gate 1 and AND gate 2, and there is AND gate 3, and there is one more AND gate 4, and there is one more OR gate as well. So there are 3 OR gates and then 4 AND gates. So and 2 NOT gates as well. So when we instantiate this in the Verilog module, let's take this examples here. This example here in the, let's see the code how it's the module, and this is simply called as a circuit with the module name, and the inputs are x1, x2, x3 and x4. The output G, H and I. You can notice that G, H and I are the outputs here. So we have combined the declarations of x1, x2, x3, and when we say output G, H, I, and we didn't give any range of bits MSB to LSB or anything, so default is 1 bit. And after the declarations, so we are also declaring this wire here. You can see what are the wires which are apart from the input and outputs. So A is one wire, and A is connecting the output of the NOT gate to the input of this gate, AND gate, and output of this NOT gate to this gate is B, and C is from here to here, connecting this 2, and D is also connecting this second OR gate to the 1. E is as E and F can be noticed here. So these are need to be declared as wire. Why not G and I? Okay, so these are outputs coming in output, so need not be declared here as wire. This is already the output. So that should be noticed, and instantiation continue, that starts here, not A. So this we are calling it as not A, that is this gate is not A, not underscore A, and the input to it is x2 and the output is A. So we follow the order of the definition of the component, that is when we instantiate this is an instance statement. So A is the output and x2 is the input, and not A is a module name which is our choice. It can be get1 or g1 or g2 or anything. So that is optional. Okay, so and the second NOT gate, similarly it is called as NOT underscore B. Okay, so the output is B over here and input is x4. So it's instantiated in the output and input order. So OR gate, which is given here as RC. So this gate, which is R underscore C, the output is C and the input is x1 and x2. So the input x1 and x2. So you can put it in any order, x2 or x1 also, that doesn't matter, that's what we had seen. So the output, you have the C. The next OR gate is, this is R underscore D. So the inputs are x3 and x4 and output is D here. And so the AND gate, next one is AND E and underscore E, which we named as AND underscore E. So the output is E and the input is x1 here and then A. So x1 and A now declared. So what the A is now known, it is declared as wire. Otherwise you will not be knowing what is the input signal which is going into the second input of this AND gate. So the next instantiation comes here as AND underscore F. F is the output again, and then inputs are, that is x3 and B. So x3 and B is now instantiate and defined or declared as wire. Okay, so we know the second input to this AND gate is B, and next AND gate comes over here. This is AND gate underscore G, where this is a G is the output. So G output and C and D are inputs. You know the importance of declaring them as wire now, C and D. Also the next gate which is over here is OR underscore I, because it's giving the output I. So the inputs are E and F, and its output is I. So E and F are here declared as wires in the structural models, which is connecting between the two hardware elements. And next one is this AND here, AND underscore H, wherein the output is H and the inputs are G and I, which are also output, declared as output. So the instantiations, as continued. So 2, 4, 6, 9 gates are instantiated. So the order in which the gates are instantiated doesn't matter. So you can put this AND gate first and this NOT gate at the last also. So because these are concurrent statements, if there is any value, supposing we have instantiated from input to output. So suppose you need, for example, if the last statement in the concurrent statement is executing, you need a value and it keeps changing the signal, and that output, suppose H here, is required for a first statement. Okay, so that H needs to be computed and then substituted in the first statement. So the simulator does this job. So it doesn't matter in which, so the last statement value is computed first and then it is substituted in the first statement. So that was the concurrency of the Verilog. So these are concurrent statements. The order in which the statements are written is not a matter. So these are instance statements, because we are calling this or instantiating this module, these small components, these AND gates, built-in gates inside a module. This is one way of this is following the instance, that is port association of format 1. Next we come to we look at the one more example of for the format 2, that is inhibit gate. So I just call this as an inhibit gate. So we can call this, so x1, an AND gate, one input is inverted. So you can call it any of this. It's simply an AND gate which with the one input inverted. So here x1 and x2 are the inputs, and there is a NOT gate over here which is now we call it as G1. That's your choice. You can call it anyway. This is not x2. So then this the wire which is here is called as not x2, and this is G2. The output is called as here out. So let's see the Verilog module for this. It's very simple, the structural model. For example, here module and the N module have this module name. We call it as G inhibit gate IH underscore G, and the inputs are x1 and x2. The output is out here, that is with closed with a bracket and the semicolon. So after this declaration, we should notice what are the other signals need to be declared here. Inputs are fine and the output is also declared, whereas one more output here, a NOT gate output, is not known to the module yet. So we need to declare what is that NOT x2 is. Okay, so the NOT x2 is going to be the wire, that it's a net type which is connecting the output of the NOT gate to the input of this AND gate, or second input. So it needs to be declared as wire in the structural model, and then comes the component instantiation. So the component instantiation, the NOT gate, NOT, and the gate name we have called it G1, and the output is NOT x2 and this input is x2. So now you can notice that it is following the output first and then the input second. So the one input, and then the instantiation of G2 comes into picture. This AND gate which has the output, this is the name or name or the component name, and out is the output, input is x1 and not x2. These are the two. So this is a small extension of the AND gate example. So in how do we call this gate in this module IHG in the other module? So that we would see. So now if we take the circuit which is having that type of gates, you can see in this particular circuit, this is one inhibit gate G1 and another inhibit gate G2 and another inhibit gate G4 in this circuit. So G3 and G4 are normal inverters there. So can in to write a Verilog module or structural module, for example, to start with, can I instantiate that previous module, which is the inhibit module, in the Verilog code which I am going to write for this particular circuit. Okay, so here, so the module, and I am going to call that module inside this module. So then how I am going to instantiate it here. So the instantiation, so how are we going to do it? So this is not a gate which is built in. So the built-in gates would follow the first format what we have learnt just now, and the second format is dot port and then the expression, local expression. So let's see that then in this Verilog code, what are the inputs? The module name, we can call it something is example here, and we have the input A and B, and the output is out 1. So just to differentiate this out of that particular inhibit gate, and here we have just named it out 1. So input A and B and this out 1. So what are the other signals needs to be declared here? So C, D, and then this not C and E are supposed to be declared. So wire C, D and not C and E are the wires which are connecting the two, making the physical connectivity between the two elements. So G2 and G3 are C, and G1 and G4 input is D here, and the G3 and G4, the first input is not C, whereas in this other one, output of G4 is connected to the G5. So this gate, I think we can call it as here name G5 instead of G3, so that G1, G2, G3, G4 it is not matching with that with not C. So now let's look at the instantiation. IHG, which is the first instantiation, I'm calling this G1. Okay, that is the previous code which we have written, the module inhibit gate G. So that gate, the module name should appear here, and the gate for which I am calling that module, this is G1. This is the module name, I am calling it here. That is that is the module name here. Okay, so G1, this is the G1. So I am calling IHG for G1 here. Okay, so now we map the port as in the case of the second format. So the format is, it is dot out, that is the first one, dot out, here that is called as D. So that dot out is called here as D. So dot, that port name was out, and D, comma, and the first input is dot x1 in the previous module, and it is now named as A. This is the local expression. This is the local expression that we have given in the format. Dot out is the component which, that is dot port name, that is this, that port name is the format is dot port name and a local expression, dot port name and local expression x1, and in this case dot port 2, that port name is x2, which is B here. So we are mapping that inhibit gate here, or we are calling that, or we are instantiating that inhibit gate in this, the first one. So you may wonder why I put it in the order out 1, x1 and x2. It need not be. So you can put it in any order in this case. It doesn't matter unless until you are correctly matching the port name. So dot out is D only. It should not be dot out is A or dot out is B. Okay, so unless and until we match that port names, the order doesn't matter here. So because it's going to be similar to the built-in gates, or so I have put it in this order. The order you can interchange as well. So now this is the gate for G1, and then the next gate is G2, IGH, G2. G2 is G2 again. This say the second time this is instantiated. So it's not that how many times you are using that same module inside this module. So you will be using three times. So the 3 times it needs to be instantiated. So that's what in the very first we have in the instantiation a module. We learned that module, top level module can instantiate the lower level module multiple times. Okay, so this is the second time we are instantiating IHG, the same gate name, and it is now the gate which for which you are using is G2. So it is, this name should be different so that there is no confusion in this. So you G1 and G2, that model name, and dot out is the same output of that gate, and dot out is now named as C. So it is mapped, dot out is mapped to C, and the input here is, first input is x1, in x1 dot x1 is now it is B. Okay, you can see the difference. In this case, the first input is A, it is mapped to A, whereas in the second gate the first input is mapped to B. Okay, and then dot x2, the second input, which is the inverted input, is A. So now A is given as here for this inverted input. So this is second time we have instantiated the one, and then we instantiate gate not C, that is G3. This is not C, and the input is C here. Okay, so this is the third instantiation, and the fourth, again the G4, we are calling it third time that previous inhibit gate, are instantiating it here IHG. The name is G4, and the dot out is the corresponding is E, and the input is, first input is here dot x1 was here not C, and the x2 dot x2 is the D, which is given here. So this is the third instantiation of the inhibit gate, and then only one is left out. Again, this we call it G5, and out one and E. Now the input is E here. So this is the 5 instantiations, 1 2 3 4 5 gates are instantiated. Again, the order of instantiation doesn't matter here, this because these are concurrent statements. So if the first, this G5 gates, E is recovering the signal first, and then suppose that E is used in the first statement of G1, then the simulator takes care of that. It is possible to, it will evaluate that and substitute, update it concurrently. So these statements are executed simultaneously. So then the order in which we write them, doesn't matter. So this example shows the instantiation of one module inside the other module with the format 2. Port association. Next, we will learn how to write the test benches for that. So for that, the previous lecture examples I have taken, this AND gate and OR gate, and how we are going to write the test bench for those things. So in the structural model of AND gate, we had this module and AND gate. The AND gate structural, input A and B and output was Y, and the AND gate is instantiated YAB. That's a built-in AND gate. So now it is very clear that output and comma input, the instantiations. And then the data flow model, in which the data flow model as the AND gate again. So where we have module, the module name and get module, input AB and output Y, and is the assigned statement A and B is assigned to Y. This is a continuous statement. This is a continuous statement. Again, what are the changes in A is immediately, and the current simulation time, whatever it is reflected in Y. So it is assigned, the Y is keep on getting the values of A and B. So it's a continuous assignment in the data flow model. So behavioral model is, of AND gate, we had yesterday or the previous lecture we had seen that AND gate behavioral, input AB and output reg. This reg declaration is used because it's always at the rate of A or B, where Y is A and B. So this is a procedural statement. We have only one procedural statement here. If we have multiple procedural statement, then the begin end needs to be, begin and block will help you to make it more appropriate in the code. So the A or B is the signals which are inputs or in the sensitivity list. The A or B is explicitly told here, this is a sensitivity list. Even in the case of data flow model, assign Y equal to A and B. So where A and B are declared, or the sensitivity list is the signals only, but that is implicit. It is here in the always block, it's given as the explicit declaration of the A and B in the sensitivity list. So this is procedural assignment. So this always block may not have sensitivity list also. So we will be looking at all those, and this always block if you have multiple always block, that will be concurrent, but within the always block, whatever the statements, if you have multiple statements, that would be executed sequentially, like any other software programming. So the test bench, now we look at the test bench. How do we write a test bench for this AND gate module? So the structural model, data flow model, or the behavioral description. So in that we have taken this structural model. So first, as its test bench is also going to be another Verilog code. So you will be writing in the text editor in the design sort. The module, which I am not showing that end module, so it is spanning over the other page. So module and the module name, now you can notice this AND gate test, that is your choice, that is the module name here again is a choice, AND gate test, AND gate TB, or some any of this would suffice. This is similar to the module name which we had learned in the Verilog code. And the inputs needs to be declared. Now that what are the inputs to the AND gate are A and B, and notice that it is reg. We are coming to this again. So it is the inputs. Now this reg A and B is going to get the input, or it is going to be driven by this. So that's why it is declared as reg A and B in the test bench, not in the actual module, Verilog module of that. So A, B, and the output is wire Y. So you can see that the output here is declared as Y. The reg and Y declarations are different in the test bench. Okay, so this wire is going to give you simply the output which we are going to verify. So in the test bench, what we do, the more stimulus, or what are the possible combinations of input A and B are, that will be test given to A and B, and then the output of the test or unit under test, the module which we are going to test this AND gate will give the output. So the next portion comes under the instantiate the unit under test. So we had looked into the instantiation. So now we are going to call the AND gate structural model inside this test bench. So the AND gate structural, this comes from our AND gate structural model module name. So this is the module name of the AND gate structural model, and then you can notice there is a unit under test. So this is going to be a name which is given over here for unit under test, and then within the bracket, so the bracket starts over here and it is ending with semicolon. So dot A and A, you can see the dot B and B, dot Y and Y. So this is, now we can relate it to the previous example. So how we called the inhibit gate inside the another digital circuit. So in that inhibit gate, the port name, that is, suppose that this is input A and input B, the AND gate input A and input B are the input A and this input B are the local expression, that is the expression related to the test bench. Okay. So this A, B are similar names are used, so do not be confused with, so that because this A, B are this A, B here. Okay. So the dot A and dot B, that is the port names of the AND gate, that is inputs, in those are inputs, and dot Y is the output of the AND gate which we have used, and this Y, so if we change them here, can change, and the A, B, Y can be changed as well. Okay. So this is a port name corresponding to the module which we are calling port names, and then these are local expressions. A, B, within the bracket what we have are the local expressions which can be easily compared with the format 2 of the instantiation just we had in the few slides back. So this is the instantiation. So now we have declared in the test bench module name of the test bench, which is different from the module which we are calling, we are going to test it, that is AND gate test, inputs and outputs. So see the declarations how it is changed, and then the module name which we are going to call over or instantiate over here, and this is optional, that is a UUT, and then A dot A port name and different port names, how many port names you have in that module. This is because we have 2 inputs and 1 output in the AND gate, so this, and these are local expressions within the bracket. So this is continuing with the initial begin. So we can see that initial is again the procedural or the behavioral description. It is executed only once, that is at initial. time. So the initial begin we are using because we have the multiple statements. So first, now the inputs, what are the inputs? A and B are initialized here. So initialize them to 0 0, and then it is not mandatory for the wait for 100 nanoseconds for global reset to finish. So it is a good practice to have this time unit specified, that is hash 100, that is this can be nanoseconds or the picoseconds, depends on the simulator time, the time set. So it can be set for nanosecond or the picoseconds. So hash 100 is a hash, signifies either here it's a time, and then it is going to be the delay, and 100 time units is the delay. If you say hash 100, it is 100 time units delay. So after this A, B are assigned to 0 0, 100 time units of delay needs to be given, and then add stimulus. So here is the important step of test bench comes into picture. So this add stimulus, what are the inputs, possible inputs can be given to the module. So one is after hash, after 100, again 100 time units, hash 100, I make this A equal to 0 and B equal to 1. So initially it is 0 0 for my AND gate, the inputs are initialized to A 0 0, the AND gate output will be 0 for 100 time units. After that, it is after 100, again 100 time units, I am just given deliberately here, hash 100, A equal to 0 and B equal to 1. I am changing the input value of A to be A equal to 0 and A 0, and B is asserted to 1. And then again, this is your choice, that second input, what are the other possible input, that A and B can be 1 and 0. So in that hash 50, so it can be some nanoseconds or picoseconds of input, you are changing that after 50, A equal to 1 and B equal to 0. So this is the next set of input or the stimulus given to the module. And the third one is the hash 50, and the other combination, the possible combination A equal to 1 and B equal to 1. The module should be thoroughly tested for all the combinations of inputs. Okay, so the 0 0 0 1 1 0 1 1. So now end this begin ends here. So the initial the one it is executed. So after 100, after 50, after 50, then it continues. Then comes the initial, and how do I see my output here? Okay, in the waveform editor, the design suite has, if you recall, that there is a template generator or the text template generator which can give the test bench template also. The text editor allows you to write it, so that you can, as we are writing the code for the module, for example in this AND gate, and the test bench for AND gate also is to be another .v file should be written. And the third part of that is how do we view the changes in the input and the corresponding output. So initial, again it is only one statement. So $monitor is again the key statement which is to observe the which is used to observe the input output change or input changes and its corresponding output. So within the bracket you can see the syntax of this $monitor, and what are the within bracket you can specify the strings and the corresponding signals as well. So the Y is the output of this, %d is signifies here that we are going to represent that Y in decimal, and %a is input, %d which is separated by comma, and B equal to %d, that is another input B is also will be represented in decimal. So /n gives the new line and within the quote. So this is the string, and now comma we have Y A B. So this Y will be assigned to this value, A is here, as well as B can be assigned to this value. So now N module, and then so we can, so this is complete test bench of the AND gate. So the first we need to give the module, and this is the N module for it, and module name, the test bench name, which doesn't have the input and output. Okay, and then specify this A and B or reg which are inputs, and the output is Y as wire, and then initialize this, the values of inputs A and B, and leave the reset to for 100 time units, and start adding the stimulus in the A B. What are the various combinations A B 00011011, all combination of inputs with some time delay, and those changes will be reflected here as the YAB, A, B, and so the monitor dollar monitor statement helps us to view that in a waveform editor. So waveform editor can give the changes in the output signal corresponding to the input. So thank you.